The goal of this particular presentation is to discuss what I have learned and what the people I've worked with have learned about how Census is implementing differential privacy for the 2020 Decennial Census. And before I start, I want to acknowledge the contributions of my co-authors. Tracy Kugler and Jonathan Schrader have played a key role in helping me and sort through what we think Census is doing. And Jose Pacas has done a great job working on some of the analysis, looking at the differentially private 1940 data that Census has released. And so I just wanted to acknowledge them. There's no way I could have done all of this on my own. Like, I would still be sitting at my desk banging my head against the computer, and so their contributions are incredibly important. So for today's presentation, we're really focused on the Decennial Census. We know that the Census Bureau is doing research on how to make the American Community Survey differentially private. We know that there are requirements for internal projects and for FSRDC projects to also use differentially private or differentially private-esque methods for the data that comes out. But this talk really focuses on decennial, because most of the documentation that Census has released has focused on that. And the goal for today's talk is to really, what I say is to demystify differential privacy. I hope to show that it's actually much less complicated than it may seem if you've looked at the Census Bureau's presentations or read some of the technical papers. And then I want to focus on how Census implemented it for the 1940 data that they released in June. And then after a break, myself and Quentin Brummett are going to be giving some short analysis results. He and I have been analyzing the 1940 data, and we'll show you what we're finding as we look at it and show the impacts that differential privacy has on the data. So how did we get here? So about a month ago, literally a year ago, tomorrow, John Abowd, Chief Scientist at the Census Bureau, published a blog post talking about how the Census Bureau needs to adopt modern disclosure avoidance methods at the Census Bureau. And this came out of a re-identification attack that Census took internally, where they re-identified 17% of the respondents of the 2010 Decennial Census. And that 17% re-identification result was shocking to them, and was really driving their now need to adopt these modern disclosure avoidance methods. A week later, John published another blog post talking about ensuring confidentiality and fitness for use. Talked about how prior methods for statistical disclosure control were opaque. The Census Bureau could not publish the swap rates. They could not publish what they did, or users could potentially back that out. This new method, differential privacy, would be more transparent. They'd be able to publish details about the noise injection parameters that they used on the data. But at the same time, there's very little discussion about the impacts on the output data, the accuracy of the output data. And so they're really focused on the confidentiality and privacy of the respondents, but very little was said at that time about how it would impact the published statistics. Shortly after John published those blog posts, Steve Ruggles, director of IPUMS and ISRDI, started really looking into the impact that differential privacy may have, particularly on the release of microdata, whether or not microdata releases could even continue under differential privacy. Could they implement it for the American Community Survey? Could they implement it for the Decennial Census? And that resulted in a December 2018 white paper laying out the implications that differential privacy may have for Census Bureau data and scientific research, and really arguing that this had the potential to really stop social science research in its tracks in the U.S. If the differential privacy methods were put in place without more engagement with the users, without Census and the users engaging over what impacts this new methodology might have on the output data. In February, Ron Jarman published a blog post on the Census Bureau where they stated that Census Bureau was adopting differential privacy for the 2020 Decennial Census. June 6th, Census Bureau releases the source code that they wrote and that they used for the 2018 census test. This is the source code that they used for the results of the 2018 Rhode Island test, and the source code that they ran over the 1940 individual level census data. So they created differentially private 1940 census data. They released that data on June 6th, along with the tens of thousands of lines of Python code that they used to implement differential privacy. Once that came out, we here at IPMS and NORC and at the Upjohn Institute have started to analyze the data. We started downloading it, seeing what kind of impacts was it having. And at that time, Kathy and Steve and I started to kind of think about this workshop. Who could we convene together to talk about the implications of differential privacy for research? 2 weeks ago, I went on vacation. I woke up in Copenhagen in a hotel, opened Twitter. First thing I saw was Steve's post saying that the Census Bureau was delaying the implementation of differential privacy for the American Community Survey until at least 2025, and that they would be engaging with users on that process and working with users to analyze the impacts that it might have. Immediately I was like, well, what does that mean for this workshop, right? We did all this work to plan this, and they're delaying ACS, but the Decennial Census is incredibly important, and they're still planning to do differential privacy for 2020, and so we need to move forward and understand the impacts that it has. The next day, I think, at the joint statistical meetings in Denver, William Sexton, who is part of John Abowd's team at Census, gave a talk where they mentioned that they were going to be publishing differentially private 2010 census data. So a few months ago, they had claimed that they did not have the resources to do it, but now they do, and hopefully by September 30th, we will have the 2010 differentially private data out so that we can compare the differentially private 2010 data with published results to see what kind of impact differential privacy is having. Now, we don't know much about that data release. We don't know what the value of epsilon is going to be. We don't know necessarily what all tables or what all geography levels are, but I think this is going to be very useful for us to analyze the impacts that it might have. John Abowd responded to Hansi Lo Wang on Twitter saying that these will be demonstration products. They will go through the full QA/QC process at Census and hopefully be available by September 30th. And then hopefully at the CNStat, the proposed CNStat workshop in December, people can come together to present analyses using that 2010 data. So what does this mean for the Decennial Census data users? So at the May NAC meeting, the National Advisory Council meeting for Census, Jason Devine gave a presentation where they talked about what products they're planning to produce for the 2020 census. And the box I've highlighted in red here are the products that they currently cannot produce because the code, the differential privacy code that they've written does not work for the detailed race and Hispanic origin tables, or they haven't found a suitable solution yet for the detailed race and Hispanic origin tables, summary file 2, the American Indian and Alaska Native summary file, and the public use microdata sample. Well, those are pretty significant data sets that a lot of people rely on for lots of research, planning, and policy purposes. And if they can't produce those now and the census starts in like 8 months and the first data come out by the end of next year, what's this timeline going to look like? Can they really finish this? Can they get all of this code implemented by the time the first data come out that are required for redistricting, for apportionment, so on and so forth? Now, public data users are going to be subject to the differential privacy aspect, but there are others as well. So people who work in the FSRDC will also be impacted by the switch to differential privacy. So in differential privacy, the Census Bureau is going to set what they call the global privacy loss budget, and that privacy loss budget is essentially fixed. Once that privacy loss budget is gone, there can't be any more data that come out. So if you're in the RDC and the global privacy loss budget for 2020 is done, and you want to bring data out for your research to further your scientific career, like you're kind of stuck. Like unless they increase the privacy loss budget, you might be out of luck. And the same thing goes for internal researchers. So people who work within the Census Bureau who do tons of great research on housing and poverty and income, what types of restrictions, they fall under the same restrictions. The privacy loss budget impacts their research as well. So we've got a lot of different stakeholders, public data users, FSRDC users, internal users, who are all going to be subject to differential privacy and the impacts that it has on data that come out. Now, there's a lot of unknowns until we really started looking into this. I think others within Census, I think others, people just don't understand what is this differential privacy thing, how does it work, what kind of impact does it have on the data? And as I started working on this, we decided that a talk like this, where we try to demystify differential privacy and show how it's implemented, is a useful product for users to understand what the impacts are. And so for the next 45 minutes or so, I'm going to go through my understanding of differential privacy and how I think Census Bureau is implementing it. Any errors or mistakes I make are mine and mine alone. They're not the other people who have helped on this. Like they're my mistakes, and I think I've got it mostly down, but I can't claim to be an expert on this. I'm not a mathematician. I don't understand all of it, but hopefully this will make sense. So ignore the fourth bullet because that's going to come later. But the main goals of this talk are to define differential privacy, how differential privacy is applied to data using a simple example, and then look at how the Census Bureau implemented differential privacy for the 1940 census. After a break, we'll come back and look at how differential privacy is impacting the data that come out of the system. So what is differential privacy? And I'm not an expert in this. I'm going to go real quick and try to get through this, but it has its roots in cryptography and in computer science. It's a formal or mathematical definition of privacy. I don't want to go through all the details on the slide, but this is effectively the mathematical definition of differential privacy. And essentially, it's a guarantee on the incremental disclosure risks of participating in a database over whatever disclosure risks the data subjects face, even if they do not participate in that database. And if you want to read more about this, I have a lot of sources in this presentation, so you can go read more of the technical documentation. But essentially, it's a guarantee over how much information is leaked about an individual when a data set is published. Every data set that gets published leaks a little bit of information about individuals. Differential privacy provides a provable bound on that risk. Differential privacy is not an algorithm for disclosure control. That's really important. It's a mathematical definition. Lots of algorithms could be implemented that are differentially private, and the Census Bureau, I think, is doing a lot of work trying to figure out what algorithms to use. But it is not monolithic. There's not just one algorithm that implements differential privacy. There's lots of ways to approach the topic. And it's not an absolute guarantee against disclosure risk. Instead, it really provides a relative guarantee against disclosure risk. So it's possible that if someone's really, really smart, they can find you in the data, period. But this provides a relative guarantee against that disclosure risk. It's a lot more complicated than that. I'm trying to distill it down to kind of how I understand it, but that's kind of the basics as I understand differential privacy. So I think as we go through the next bits and look at how it's implemented, kind of shows the mechanics of it help illustrate a lot of these issues. So I'm going to work through a toy example that Tracy and I developed in June to kind of show how differential privacy is implemented. And the algorithm that I'm about to describe is about the most naive implementation you can have. This is the kind of at a most basic level, this is how differential privacy works. So in this toy example, we start with true microdata. So let's say you've taken a survey of, in this case, 100 individuals, and we have two variables. We have sex and we have school attendance. Sex can take two values, male and female. School attendance can take on three values: never attended, currently attending, or attended school in the past. We take that true microdata and we construct a cross-tabulation from that true data. So now we have a 3x2 cross-tabulation with 6 cells. We have the male never attending, male attending, and male who attended in the past. You see the crosstabs here. We have a population of 100 individuals in the survey. We have this cross-tabulation now. We define a Laplace distribution with whose spread is determined by a value epsilon, and we'll get into this a little bit more later. From that Laplace distribution, we draw a random number. We draw a random value from that distribution for each cell in the crosstab. So we draw 6 different random draws, and we add that value to the cross-tabulation. So here you can see that we subtracted 1 from the males who never attended school, but we didn't change the value of male who are currently attending school. You can see that the females who have never attended schools went from 4 to 12. The magnitude of the noise that we infuse is independent of the values of the cross-tabulation. The noise is simply dependent on the shape of that Laplace distribution. So there's no relationship between the magnitude in the cell and the noise that's infused. That's how you can see a 3x increase in the female never attending cell. The other thing you can see is that we've now gone from 100 respondents to 108. So we're not enforcing any constraints. We're not enforcing any what are called invariants in this. We're simply, saying we now have 108 respondents. So now you could stop here. If you just wanted to have the cross-tabulation, we have what we call a differentially private cross-tabulation. And maybe you just want to use the table for your research. You can also take this particular table and construct synthetic microdata out of the values of in the cells. So now we have synthetic microdata that sums up to 108 individuals with the characteristics of these people. There's no longer a one-to-one relationship between the 100 people who fill out the survey and the synthetic microdata that we've created. We've created 8 extra people, and we may have done a little bit of tweaking to the magnitude of those other cells. So there is no longer that one-to-one relationship. If we look at the true values versus the noise-infused table, again, just revisiting that, you can see that the values, again, can stay the same, but they can also change quite dramatically. And as we worked through this, we're like, oh, this could have major implications for research and policy purposes. So now that I've kind of walked through a very simple example, I want to talk about how Census Bureau is implementing differential privacy for the 1940 census and for the 2020 census, and talk through the decision-making process that we think they're going to go through, and how there's a split between the policy decisions that have to be made and the technical implementation that they'll go through. And I want to emphasize the importance of both of these pieces of the puzzle. The policy decisions inform the technical implementation, which we'll talk about, and the technical implementation requires particular inputs, which are the outcome of this decision-making process. So the key takeaway from this particular part of the talk are that the policy decisions are going to be made by a group of people. They're going to be made by the Data Stewardship Executive Policy Committee, which is chaired by Ron Jarman, the Chief Operating Officer of the Census. And they are going to sit in a room similar to the one we're in now, and they are going to decide what the global privacy loss budget is for the 2020 census. They're going to decide how to allocate that privacy loss budget to the tables and the geographic levels in the 2020 census. And I think one of the questions we have as a group is like, what stakeholder input are they taking as they make this decision? There's lots of different ways to divide up that global privacy loss budget. Who is getting a seat at the table? Who are the stakeholders they're engaging with to help understand the potential implications that this allocation process has, and how are they going to be, reaching out to users to get that information? There's 4 policy decisions that have to be made. They have to decide on the global privacy loss budget, the geographic levels that they're going to allocate the privacy loss budget to. They're going to have to figure out what fraction of the privacy loss budget they need to allocate to each of those geographic levels. They can choose how that allocation will happen. They choose the tables that receive portions of the global privacy loss budget, and what fraction of that privacy budget is allocated to each of those tables. And the final thing they need to decide on is what are the invariants or the constraints that they are going to put into the system. So I want to talk about this right now. This is, I think, a key issue that is going to come up in a lot of our conversations today. But essentially, invariants are counts that they will not infuse noise into. So these are going to be the counts that are going to be true, and that there will be no noise infused into them. Well, the minute that the Census Bureau publishes an invariant, that weakens the privacy guarantee provided by differential privacy. And some might argue that the data are no longer differentially private once you publish an invariant. And so the question is going to become, what invariants are they going to go for? At this point in time, we're pretty sure that the state level total population count will be invariant, because that is what's required for apportionment purposes. But there's a chance that no other counts will be made invariant. This is very different from the 2010 census, when census block total population census block group quarters population, census block voting age population were all invariant. So at the census block level, you knew the exact population count for that unit. Then you could roll those up. You could aggregate those to places or voting districts or Alaska and American Indian lands and know what the true population count was for those entities. If that block population count is no longer invariant, there will be noise infused into that count. And as you roll those up, you might be getting a value that is no longer representative of the count. We think that's fundamentally important because for a lot of small places, the decennial census is the best source for demographic information about who lives in those communities. The ACS is a sample. They pool 5 years worth of data. The margins of error on some of those estimates are pretty wide. And then you don't really know what's going on. The decennial census has for a long time been that sole source of really high quality information. If they're infusing noise into these counts, what's a town of 500 people? Is it 500 people plus or minus 100? What does that look like? How do they plan appropriately for resources? How do they plan for schools? How do they plan for all of these things if the quality of the data that are coming out of the system is not high enough for the use cases that they have? So what's the technical implementation of this look like? I'm going to talk through an example, and this is focused on what they did for the 1940 complete count census data that they published. So we're going to walk through that and show you how they did this allocation, how they chose the geographic levels, how they chose the tables, and how they did their noise injection. So they start with the census edited file. So this is the file that the Census Bureau will produce. So they'll take all of our census responses and they'll edit those data. They will do logical edits, so you can't have a 4-year-old who's the head of the household. They will do imputations. They will do whole household imputations. They will impute items that the person didn't fill out. And after they've created the census edited file, they will pass that through their disclosure avoidance system, or the DAS, as Census calls it. That's where differential privacy will be implemented. The output of the DAS is what's called the microdata detail file. That is the differentially private individual level data that are produced. That microdata detail file will then be the input to the tabulation software that creates PL 94-171 for redistricting, that creates summary file 1 from the 2020 census, and that would create other types of products that will come out of the 2020 census. So in thinking about this, as I talk more, think of the census edited file as truth, or as true as any data set can be. It's the gold standard against which we will compare differentially private information. The microdata detail file is really synthetic. There is no one-to-one relationship between the microdata detail file and the census edited file after it's gone through the disclosure avoidance system. In our example, the 1940 complete count data from IPMS is the equivalent of the census edited file. The differentially private 1940 complete count data is the equivalent of the microdata detail file that census will produce. And these are the terms, the CEF and the MDF, that's the terms that census uses to describe these products. Now within that disclosure avoidance system, there's really 3 parts to the process. They have to define the geographic levels and the tables that they want to include in the disclosure avoidance system software. They have to decide on the privacy loss budget and how that privacy loss budget is allocated to the tables and the geographic levels. And they have to do the noise injection. So they have to actually infuse the noise into the data and then get the output. So let's talk through each of these 3 in a little bit more detail. So let's talk about geographic levels and tables. In our toy example, we have one geographic level. It could be a county, it could be a census tract. We have one geographic level, and we have one table. In the 1940 data, it's a little more complicated. The Census Bureau in the software, they have 4 different geographic levels. They have the nation, the state, the county, and the enumeration district. And these nest within each other. So enumeration districts nest within counties, counties nest within states, states nest within the nation. For the tables, these are cross tabulations of microdata variables. For 1940, there are 3 tables that they allocated privacy loss budget to.
Yeah, Larry talked yesterday. Tell me more what's involved before I commit fully, I guess.
Can you just repeat it? All right. Voting age by Hispanic by race. The voting age, this is a 2 by 2 by 6 cell table. So there's 2 voting age, either above or below age 18, 2 Hispanic, yes or no, and 6 race categories: white, African American, American Indian, Chinese, Japanese, and other Asian. Those are the 6 race categories in 1940. So 24 cell table. This is just the enumeration of each of those possible combinations. They have a household and group quarters type table that has 8 different categories within it. And finally, they have what they call the detailed tables. This is the full cross-tabulation of those 4 variables, 2 by 2 by 6 by 8 for 192 cell table. Once they define the geographic levels, they choose those. Once they choose the tables, they then have to allocate this privacy loss budget to each of those geographic levels and each of those tables. So in 1940, the Census Bureau simply allocated the fraction of the privacy loss budget as 0.25 to each of the 4 geographic levels, just an even split across all those geographic levels, summing to 1. The fractions always have to sum to 1. For the 3 tables they chose to include in their software run, and VHR is that voting age Hispanic race, HHGQ is the household group quarters, and detailed is that 192 cell table. They allocated the fractions as 0.675 to VHR, 0.225 to HHGQ, and 0.1 to detailed. There's no theoretical justification for this allocation. They just decided this is how we're going to allocate the privacy loss budget to each of these tables and geographic levels. They then take the cross product of the geographic levels by the tables to decide what's the fraction of the privacy loss budget that gets allocated to each combination of geography and table. So we take the geographic levels and the tables. We have 1 table for each geographic level. We add in the fractions that they allocated, and we simply multiply those together. Okay? That is the fraction for each record there. That's the fraction of the privacy loss budget that's allocated to each geographic level table combination. Still sums to 1, and the higher the value in that table. So if we look at the nation VHR option, we see that it gets 0.16875 of the fraction. The key thing to keep in mind today is that the higher that fraction is, the less noise gets injected into that table. The less noise that's injected means that is more accurate. That is more accuracy is allowed. They're infusing less noise. That means that table is going to be more accurate. You can see that detailed table is getting 0.025 of the privacy loss budget. That means that it is going to get the most noise infused into it, and that is going to be the less accurate table that comes out. The data is going to be less accurate than we had. Okay, so we've got geographic levels and they have a fraction. We've got tables, they have fractions. We have this cross product. We now know how much of the privacy loss budget gets assigned. But you'll notice we haven't talked at all about what is the actual privacy loss budget. These 2 things are decided on independently from one another, right? We're going to see how those interrelate in a second, but the fractions are decided kind of by the left hand, but the right hand can make a decision on the privacy loss budget, and they don't necessarily have to relate to one another. They don't relate to one another. So now let's talk about that global privacy loss budget and what that looks like. The key thing to keep in mind here, and we've got a parameter epsilon, and I'll probably say epsilon a few times. That is what the differential privacy literature calls the global privacy loss budget. There's an inverse relationship. The smaller the value of epsilon that we see, the more noise gets infused, the less accurate the output data are. The larger epsilon is, the less noise gets infused, the more accurate the resulting data will be. And again, this value, you're not going to run a computer program to get this value. A group of people is going to sit in a room and choose what the global privacy loss budget is for the 2020 census. That epsilon value is very important because epsilon controls the spread of the distribution that's used to generate the random noise counts. So the width of this Laplace curve is determined by that value of epsilon. The wider that curve is, the wider the tails are, potentially you could draw a random number from those tails, infusing or injecting a lot of noise into a resulting count. total epsilon, the global privacy budget, is the sum of the epsilon values that are assigned to each geographic level table combination. And the epsilon assigned to a geographic level table combination is simply the product of the global privacy budget times the fraction assigned to that geographic level table combination that we saw before. So what does this look like arithmetically? So here, revisiting the table I had shown earlier, we have a set of geog level table combinations, and we have the fraction assigned to each of those. We choose a global privacy budget. In my example, we have a privacy budget of 0.25, and we simply multiply the fraction, the geog table fraction by that global privacy budget to get the epsilon geog table value. And that is then used to generate the dispersion parameter for the Laplace curve that they use to infuse the noise. Now, the key thing to know here is that the sum of all of those epsilon geog table rows must sum to the global privacy budget. So it's 0.25. If you add up all those numbers, I'm pretty sure you get 0.25. And that is essentially the mechanics of how the process works for deciding what these noise infusion curves are going to look like. After that's done, they actually do the noise injection. So going back to our toy example, the noise injection is really represented here by the red values, the -1, the +8, the -2, etc. So for purposes of nice plots and easy explanation, all the examples I talked about use the Laplace distribution for the noise injection. The Laplace distribution is really to be used for continuous variables. The Census Bureau actually uses a geometric distribution for count queries, which are all the data that we're going to be looking at today. But at the extreme, the geometric distribution looks equivalent to the Laplace distribution, and I really like the curves look much nicer when you're making Laplace plots, so we've gone with that. So it has centered on a mean. That mean is usually 0. It does not have to be, but it's usually 0. And the spread is determined by that dispersion parameter whose value is controlled by epsilon geog table. Now there's another formula you have to implement to get the actual dispersion parameter, but that's a little more detail than I want to go into today. This is what that Laplace distribution curve would look like, and in this case, the dispersion parameter for this is 47.4. That's the dispersion, and this will make more sense in a second. The key thing to know is that 90% of all random draws out of this particular Laplace curve will be plus or minus 76. So the values will range from -76 to positive 76. 99% of all random draws will range between -185 and positive 185. I've now put 3 Laplace curves on this particular chart, and the key thing to take away from here is that the more peaked that Laplace curve is, the more accurate the values are. It means that the random draws can't really fall out into those tails. The black line that I've labeled less accurate has a much wider dispersion parameter. In this case, it's actually 320. And that means that if you're drawing random values from that particular Laplace curve, you could end up far out in those tails of plus or minus 500 or 750, which is a fairly large amount of noise you could be infusing at the block group or tract level. Now, the reason these are important is because these are the actual Laplace curves that Census Bureau would have generated for the 1940 data that they published under a global privacy loss budget of 0.25. So the red line represents the noise curve for the voting age Hispanic race table. The blue curve is the noise that they would have drawn for the HHGQ table, and the black line, the most spread apart line, is the Laplace curve for the detailed table that they developed. As epsilon, if the global privacy loss budget grows, so goes from 0.25 to say 4, all of these curves will essentially get narrower, right? The spread will decline, and the possible numbers you can draw out will shrink. It's going a lot faster today than I thought. It's good. So what does this actually look like in practice? So now I want to walk through how Census is implementing this, or what my take on it is. It's really a two-step process. So the Census Bureau first creates essentially synthetic microdata that have no geographic identifiers on it. We simply know that all of these synthetic individuals are in the U.S. That's the most that we know. After that, they go through an iterative process where they assign geographic identifiers to each of those microdata records using a constrained optimization process, using a commercial optimizer called Garobi. So let's walk through each of these two steps in more detail. So in step one, they'll take the census edited file and they'll create a national table from that true data. So whatever tables they've defined, in this case they have VHR, they have the household group quarters, and they have the detail table. They'll create those three tables from the true data for each cell in that table. So we've got one geographic level and we've got 192 plus 8 plus 24 cells. They'll draw random values from the Laplace distribution for each of those cells, and they'll add that value to the count for that cell. Once that's done, they will generate synthetic microdata with no geographic identifiers from the output of step two. So they've infused the noise into these national level true counts, and they create individual person records out of that particular data set. And it's probably a lot more complicated than that, but at the most fundamental level, that's what they'll do. So that's step one. So the output from step one will then be used in these parts of step two. So in step two, they move down one level of the geographic hierarchy to the state, and they create a state table from the true data. So in this case, they'll create a VHR, an HHGQ, and a detailed table for each state in the U.S. For each cell in that state table, and now we're at 51 states times the number of cells in the national table, they'll infuse noise drawn from these distribution curves into those cells. And they'll then use Garobi to do a constrained optimization to fit that step one microdata. So the outcome of step one will be fit into those noisy state cells. So they will do, a bunch of complicated linear programming to essentially say, okay, I'm going to assign this person to Alabama, I'm going to assign this person to Minnesota, this person goes to New York, based on the values in these state cells. And they use the stopping rules that are built into Garobi. They have not written any custom code for what is the best fit. They use this commercial product to decide what the stopping rules are. After they've done that optimization, they then assign a state identifier to each of those step one microdata records. So they've done this process, and now each record in the step one microdata has a state code on it. They haven't changed any of the other bits of information on the record, but they've assigned a state code to that person. They then repeat steps 1 through 4 for the remaining geographic level. So they then move down to the county level, and they create a true table, a table from the true data at the county level. And they then infuse noise, and then they run another linear optimization step where they now assign a county identifier to each case in the data set. And then they do the same thing for enumeration districts. And then they do a post-processing step, which Nicholas pointed out, and again, a good catch on that, to make sure that they can enforce consistency so that enumeration districts add up to counties and counties add up to states, and the marginal totals add up to what they're supposed to. So the output of this process is a microdata set with an individual record for each person in the census, and it now has a state, a county, and an enumeration district identifier for each of those individuals. The process does not change the characteristics of individual people, so they don't make males into female, or they don't change the age of a respondent. They simply are assigning these geographic values to them. But remember that the output of step one microdata is already synthetic, right? So these are already fake people, but they are not changing the characteristics of any of those records. Okay, At the most basic level, that's what we think census is doing for the 1940 census, and that's the type of process they will go through for the 2020 decennial census. Now, I think yesterday we mostly came to the agreement that others in this room agree, and others on the phone, that that's essentially what census has done for 40 and what the plan is for 2020. So now let's talk about the unknowns or the things I don't understand related to this. And there's more than I'm going to enumerate now, but I think these are kind of big picture things that are important for us to consider. Now, I'm not the smartest guy in the world, but these are the things that I'm just think are fundamentally important for us to think about going forward. So one, what role will invariance play in 2020? In a recent paper released by Ashmead et al., who are at Census, they looked at how much invariance we can, or can you even quantify the loss of privacy once you've published an invariance? As it turns out, you can't. It's unquantifiable without making assumptions about the knowledge of the person who's trying to re-identify the data. So you have to know something. You have to make assumptions about that to quantify the loss of privacy once you've published an invariance. And so invariants make the Census Bureau's life very, very, very difficult. And my guess is they will try to have very, very few invariants in the 2020 census because it means they can't provide a provable guarantee of privacy, and it makes their code much more complicated. It makes it a lot harder to run these optimization steps if they have these invariants in the process. These were the invariants in 2000 and 2010 at the block level, just showing that invariants have long, for small geographic levels, have long been part of the Census Bureau's process. In 1990, race was also invariant at the block level, according to one of John Abowd's presentations he gave at a FESAC or a CSAC meeting. The other thing that is an unknown yet, household person join tables. So an example of this would be the number of children living in household headed by a single female. As of today, that product cannot be created with the current top-down algorithm that they've developed. And I'm sure they're working on it, but as of today, a year out from when the data are supposed to come out, they cannot create that. Detailed race and AIAN are also currently out of scope for the top-down algorithm. I don't think that's because they can't run it. I think it's because the results that come out for these detailed race and ethnicity tables are potentially quite bad and inaccurate, and that they would be very worried about publishing those data sets. And from I'm not a family demographer. There are many of them in this room. These household person join tables are incredibly important to know what is the neighborhood context. Is this a neighborhood of lots of single female-headed households with children? Are there lots of same-sex married couples in this neighborhood? To learn about how the family structure of the U.S. is changing, these are really, really important tables. And if the Bureau can't produce them or are not going to produce them, that's a real loss to the research community. Inheritance of accuracy. So according to the Census Bureau, the accuracy of the output counts as you move down the hierarchy, the county data inherits some of the accuracy at the state level, and the enumeration districts inherit the accuracy from the county level. Truthfully, I still don't get this. I don't quite understand what they mean when they talk about this. But according to some emails I've had with people at Census, some of the results you'll see later are misleading because the enumeration districts are actually more accurate than some of the results I'm providing are. It's very weird. And so this is something I think that is important for us as a research community to kind of get our heads wrapped around. The final thing that I think is super important are what we're calling off-spine geographic levels. So this is the standard geographic hierarchy that the Census Bureau creates summary data for each of these different geographic levels and for each unit within these geographic levels. Thus far, the differential privacy work that they've done is really focused on what we call the central spine. So states, counties, census tracts, block groups, and census blocks. The top-down algorithm really moves down that hierarchy. But as you can see, there's a whole lot more geographic levels that are off that spine. And importantly, a lot of those geographic levels actually have units that are really, really small. So for example, in 2010, for places, census data places and incorporated places, the median population in the US is 1,041 people for census places. Census block group median population is 1,240 people in 2010. So the amount of noise that would get infused in a census block group is equivalent at the median to what would get infused at the median place level. The data, you'll see this in a little bit, from 1940, the median population for enumeration districts in 1940 is about 840 people. So the noise that you're going to see in a little bit, the noise that was infused, can be kind of made equivalent to block groups and to places in 2010. And again, as I said before, for a lot of these small places, the decennial census is the most reliable and only reliable data set that comes out. And if we're infusing noise into these counts, what does that mean for the people that live in these places, for the policymakers, for the leaders of these places? Okay, so couple of conclusions before we move. I don't know what my timing looks like. We go through 10:45. Okay. All right. So in conclusion, what I hope I've done here is tried to demystify differential privacy, and I think it's actually less complicated than I expected. When I first started reading this in the fall, when Steve was working on the white paper, I would read these papers and I was like, my eyes would glaze over. All I would see were formulas and proofs and algorithms for how it was done. Once we actually saw the data and could kind of work out the arithmetic, all of a sudden it started just, a lot of kind of things clicked in my head. And I think those arithmetic tables were just doing some multiplication and then generating these distribution curves. That's really what kind of like, oh, it's actually not as complicated as census maybe makes it out to be, either because they're trying to be willful about that obfuscation, or if they're just not used to talking to data users about differential privacy, and they're mostly used to talking to people who work in the field, either computer scientists or statisticians or cryptographers who that, and they're used to thinking about things from the algorithmic or mathematical perspective. I hope this presentation has demystified that a little bit. The second conclusion, and I think is really important, is the fundamental importance of those policy decisions. So this is not just a technical solution to a problem. There's also a ton of policy decisions that are going to go into this, and who gets to make that decision? Again, what information are they going to be taking in as they decide on the global privacy loss budget? As they allocate that global privacy loss budget to geographic levels and tables, there could be, things really get inaccurate if they are deciding to not allocate certain pieces privacy loss budget to certain geographic levels, or they privilege some set of tables over another. How are they taking that information into account? Who are they engaging with? And what can we do as a user community to engage with census and push for transparency in that decision-making process? So that's the end of this talk, and I think we'll have time for some questions. What I will say is that when I put these slides out, I have kind of a short bibliography of the references that I have looked at, and I think Jonathan, Tracy, and Jose and others have read, that really helped inform the presentation that I just gave. And I want to kind of highlight a couple of papers in here. The final one on this slide by Dana Boyd was just published in July, I think, and she tries to, kind of similar to what I've done, really kind of step back a little bit and look at this from a more policy and user perspective, and who knows about this, how is census engaging, where are things kind of breaking down in that communication strategy, and it's a very, I think, approachable paper. The Bambauer et al. Paper, Fool's Gold, is really a critique of differential privacy, trying to show its limitations. Another useful paper. And if you want to learn about how this works, the Jerry Ryder paper, the 2019 Ryder paper, Differential Privacy and Federal Data Releases, is also, I think, a very approachable introduction to differential privacy and its potential impact for federal data products that are coming out. And I think he does a very good job of talking about the implications that this will have for users and for the Census Bureau moving forward. The final thing I want to do is I just want to mention Phil Leclerc, who wrote one of these papers. Phil is a programmer who works in John Abowd's shop. He and I had a really long email chain back in early June where I was writing to him, asking him am I understanding this correctly? And he was really generous in writing back some really long emails, kind of walking me through where I didn't understand things and trying to clarify a lot of those pieces of information. And I think without that input, we wouldn't be as far as we are now in understanding. Okay, I want to go ahead and get started here with the next little bit. I'm going to try to go through these fairly quickly. Many people have seen these before, and then give Quentin enough time to do his presentation. So I want to show some of the results that I've found when analyzing the differentially private 1940 census data that came out in June. Just a little background. The Bureau released the differentially private data on June 6, 2019. They chose 8 different global privacy loss budget levels for those data sets, 8 different values of epsilon. Those values ranged from 0.25 to 8. So an epsilon value of 8 means there's very little noise infused, so the data are more accurate. Privacy loss budget of 0.25 is low, which means there's a lot of noise infused into the data, and that is going to be less accurate. So just to bracket that for understanding. For each of those different values of epsilon, they did 4 different runs. So they ran the data file for 0.25 4 different times. And what that helps you do is get at what's the variation for each of the point estimates. It kind of helps you think about what's the margin of error or the error around each published data point. Wish I had 1,000 runs to get a better distribution, but we have 4, which is actually pretty helpful. Now, we have not done much work at all analyzing the run-to-run variation. The results I'm going to show you today are really focused on what they call run 1 for the different levels of epsilon. But I think going forward, we want to look at that run-to-run variation if possible. So what do these data look like? So it's actually the equivalent of the microdata detail file. Each record is an individual, or in the unit file, it's a housing unit. These are the state, county, and enumeration district identifiers that are on each of the records. Here we have a privatized unit identifier and person number, along with the record type, whether or not it's a housing unit or a group quarter. Here we have the voting age, race, and ethnicity variables. So voting age can take 2 categories, above or below 18. Race can take on 6 values, and ethnicity can take on 2, either Hispanic or not Hispanic. And most of the files, a bunch of nots. So when I opened this file, I was really hoping we were going to get income, we were going to get employment status, we were going to get educational attainments, and we didn't. And a lot of these 9s represent the other variables that they did not include in their optimization program. They did not protect with part of the privacy loss budget. So all the analyses I'm going to show today are really based on these very small set of demographic variables that they actually have published in the 1940 data. So just to recap, we have state, county, and enumeration district. We have voting age, Hispanic, and race, and we have group quarters type. So my analysis focuses on total population, voting age, actually African-American population, and a little bit of segregation. We thought I would have fixed this slide last night, but I didn't, for counties and EDs. So the comparison that I'm doing here is I'm comparing what I call the true data. Those are the IPM's 1940 complete count data and the differentially private data that Census has put out. And we really want to examine the impact that noise injection has on counts, percentages, and segregation, and then we've done some regressions using the individual level microdata as well. I'll talk a little bit about that at the end. Really, the key takeaways are this. The smaller a population gets, either a smaller geographic unit or a smaller subpopulation, even if it's in a fairly populous geographic unit, the smaller the subpopulations are, the less accurate the counts are. Now, Census Bureau would say, that's great. That's exactly the way this algorithm is supposed to work, because those small subpopulations are at more risk of re-identification, and we should protect them. And I would say, those are the subpopulations that this data are used to study, and that we actually want to know good information about those subpopulations. And if you're infusing all this noise into them to protect them, how is that reducing the utility of the data to actually study these small groups? And so, as you'll see in a lot of these slides, the more we slice and dice the people, the less accurate the resulting data are going to be. So let's just do some basic distributional assessment just to show that the data that come out of the differentially private algorithm actually look pretty similar at the grand scale to IPM. So these are box plots just showing the distribution of total population for the 3,100 counties that are in the data set. The red box plot on the left is true. That's IPM's data. Each other box plot from my left to right, I don't even know what direction that would be for y'all, 0.25 on the left over to 8. Each of those is a different global privacy loss budget that census used. And you can see at the county level, just the overall total population distribution is essentially equivalent. The one thing you see is that at the 0.25, the minimum value is more like 100 in that slide, but the actual minimum population in the true data is 37. Loving County, Texas, the smallest county in America by population, has 37 people in it. The largest county is 4 million. It's Brooklyn in 1940. This is the distribution of total population for the enumeration districts based on values of epsilon. Again, the red box plot is IPM's, and each subsequent column is a different value of epsilon. Again, we can see fairly similar distributions. There are 134,700 EDs in 1940. The minimum population is 1. The maximum is 16,000, and the median is 866. Remember what I said before, place median in 2010 is about 1,000, and the block group median in 2010 is 1,240. So the EDs are kind of equivalent-ish to block groups in 2010. So plotting this now, you're going to see a lot of these plots, so I want to orient everybody to what these look like. On the x-axis, we have the total population count as derived from IPMs. So that's our true value. On the y-axis, we have the total population count as computed from the differentially private data that Census has produced. And each panel is a different global privacy loss budget for the values. Each dot then is a county, and you can see, once you're up to a value of 8.0, you're really pretty much the noise-infused counts are coming very close to the true counts, and you see a little bit of variation around that line at 0.25 for smaller counties. As we break this down by enumeration district, here again we see the IPM's count on the x-axis, the Census Bureau count on the y-axis, and now we can see how that noise injection is impacting these smaller geographic units. So anything off the diagonal here is either IPM's has a larger count or the Census Bureau has a larger count, and a couple of things to pay attention to. If you look at that 0.25 plot in the upper left-hand corner, hopefully you see that there's a positive upward bias at the ED counts. There's more kind of dots for small EDs above that line. That's because they enforce non-negativity. So remember I was saying that these noise infusions that can be drawn could lead you to have negative people in an enumeration district. One of the constraints that they impose is they do not allow that to happen. So they end up kind of giving a positive upward bias to some of the small entities, and you can't see it here, but there's a negative bias for larger entities. They're kind of offsetting one another. We can't lose any people, right? We have 138 million people in 1940. We're not going to kill anybody off with differential privacy. We're going to maintain that count going forward. But you're going to see plots that look a lot like this for the rest of my talk, because this is essentially what's happening with the noise infusion. This plot shows the difference. So I simply took the difference between IPM's, the true data, and the differentially private data, and I've done box plots here looking at that difference. The orange is for counties, and the teal as at the enumeration district level. Here you can see that the magnitude of the noise is essentially independent of the geographic unit. So you're infusing similar amounts of noise both at the ED level and the county level. That's how differential privacy is supposed to work. Your distribution controls what types of values you can randomly draw, and you simply add or subtract those to the geographic unit, regardless of the count that's in that geographic unit at all. And this proves that the algorithm is working as it should. As the value of epsilon grows, as we move towards 8, the difference reduces, right? So you're getting more accurate data out. The difference between IPMs and the differentially private data are staying the same. But for lower values of epsilon, you're kind of seeing you're getting fairly high the magnitude of error. So now I'm going to walk through 3 different sets of tabular summaries for non-voting age population, for African Americans, and for segregation. And for everybody who saw these yesterday, I cut out some of the slides, so we don't have quite as many of the results as I showed yesterday, but I did that to hopefully save a little bit of time. So non-voting age population, this is for persons under the age of 18. This is a simple scatter plot of the counts of people under the age of 18. At the county level, this looks very similar to what we saw for the total population. This is the scatter plot at the enumeration district level. And here you can see that we have a number of cases where, especially for lower values of epsilon, where IPMs shows no individuals who are under the age of 18, and the differentially private data are showing people who are 18 and over in that enumeration district. And then the converse, the differentially private data there's a 0 count for some enumeration districts, and IPMs is showing up to over 100 people who are under the age of 18 in that ED. This just shows the scatter plot of the percentages of the population who are under the age of 18 at the county level. Here you see some interesting cases where differentially private data produced a couple of dots that I know they're a little hard to see, where there are 0 people under the age of 18, and IPMs has a value of over 20%. So you're seeing kind of how that off diagonal can come about. But here's my favorite plot that I talked about yesterday. This is the percentage of the population under age 18 by enumeration district. So I've restricted this plot to EDs containing 50 or more individuals, just to get rid of a lot of those really small EDs. And again, just computing that difference. And I want to draw your attention to these dots along the top axis. So these are enumeration districts that the differential privacy system has created, where all people in that ED are under the age of 18. 100% of those people are. Now, I don't know about you, but that is effectively impossible. Find me an ED in this country where 100% of the people are under the age of 18. Maybe 1 or 2 juvenile detention facilities, but they're probably going to have people who work there who are over the age of 18. This is very unlikely to happen, and this is just kind of showing what kind of impact differential privacy can have for some of these interesting, subdivisions of the population. Thinking about African Americans, this is the scatter plot at the county level. Now, I think this is a useful slide to spend a second on. So we looked at the non-voting age scatter plot of counts, and you saw that scatter plot actually was, you didn't see a lot of variation around the line for small values of epsilon. Now we're subdividing the population a little bit farther. We've got a lot of counties in the U.S. in 1940 that had fairly small African American populations, and you're infusing that noise into that count, and now you're seeing more spread, more variation around that line, even up to values of 8. Now we're talking about a magnitude of 10 in the case of the epsilon of 8. But if we look at the 0.25, we've got cases where the differentially private data are saying there are 500 or so people or 100 or so people in a county when it was 0, and it's even crazier for enumeration districts, where we have cases where there are approximately, over almost 500 people in an ED who are African American, and the true data are 0. So again, as we subdivide the population down into either geographic units or by subpopulation group, that noise infusion is introducing more inaccuracy into the counts, and potentially really compromising these data for research purposes. This is just a simple scatter plot of the percentage of the population who are African American by ED. Kind of similar to the non-voting age population, but you can see that the variation is still there's still a lot of noise in that data. That's at a nationwide scale. It kind of maybe covers up some state-to-state variation. So now I've highlighted all of the New York enumeration districts that contain 50 or more people. And I just wanted to see kind of how similar the distribution of these percentages were for New York EDs compared to the nation. And really, in this case, I'd say that the New York case is fairly similar to the nationwide case. The scatter plots are somewhat similar. This is for Alabama EDs. So these are the percentage of the population who are African American within the EDs in Alabama in 1940. Again, these are kind of following the general pattern of the country. And I couldn't go by without doing something for Minnesota. So these are the percentages of the population within Minnesota. And Minnesota did not have a lot of African Americans in the 1940 census. And here you see, more cases where the true data are showing 0% of the population having EDs having that, and the differentially private data kind of injecting noise and saying that there were African Americans in those EDs when there really weren't. Finally, I want to just talk about some segregation metrics, or a entropy index, which is not really segregation, but close enough for this talk. I'm using just the P log P entropy. It's a 4-group entropy calculation. We have whites, African Americans, American Indians, and Asians. So I collapsed Chinese, Japanese, and other Asians down into a single group. Computed the proportion of each of those within an enumeration district, multiplied it by the log of 1 over that proportion, and then I summed those and divided by the log of 4 to give us a basic diversity index for each ED in the country, following Iceland's census paper. And so here we see the 4-group diversity index for enumeration districts containing 50 or more individuals. And I think here you can see that, even up to epsilons of 1 or 2, as we compute these diversity indexes, you're getting a lot of inaccuracy. The noise infusion is really giving you some interesting results. And then the other interpretation to make of this is that 0 is that the ED consists of 1 race group, 1 only, and a value of 1 is that the population is split perfectly. So 25% of the ED's population is for each of those race groups. This was the plot that I made at my desk a month ago. Like my jaw kind of hit the desk. I was like, oh wow, like this is potentially problematic for one of the fundamental research areas in sociology that's been done for a very long time. And what does this mean for residential segregation research going forward? If we restrict our analysis to only EDs containing 500 or more persons, so really dropping out those small EDs, you still see a lot of variation for ad values, even up to 8, you're getting some variation, especially at the low end. Finally, just for completeness' sake, I did the same diversity index for counties. And you can see some spread for lower values epsilon. This is a research thread that we're going to keep moving on. We want to do more with the segregation computations to see what kind of impact the differential privacy has for dissimilarity and for other types of segregation indexes that we can calculate. Finally, just to talk about some of the regressions that Jose helpfully worked on with me over the last couple of months. So we wanted to use the microdata in some way to see if we could look at some regressions, because that's a common use case for census data. So we ran this regression for each state and for the whole country, for each level of epsilon. We predicted voting age by race, by Hispanic ethnicity, and by the interactions between Hispanic and race. It's a fully specified regression model. Got 138 million cases at the nationwide level, and we wanted to look at what these beta coefficients look like at the nationwide level and then by state to see how much the noise might be impacting the outputs of these regressions. So here's the coefficients from that regression model for the whole country, for all data in the US. You can see that, and each colored dot is a different level of epsilon. The leftmost dot is IPMs, the true data. Here you can see that for the individual race values, the point estimates for those beta coefficients is fairly similar. You've got so many cases, the errors are quite small. As you move into the interactions, though, you see a lot more variability in those regression coefficients, and you have cases like for Chinese, Japanese, and Hispanic, where the true data is positive and significant, and the differentially private data for the 0.25 is negative and not significant, a different significant from zero. This was just kind of our first crack at what does it look like to analyze these data at the microdata level. So then, after doing the nationwide, we wanted to figure out what this looked like at the state level. So we ran that same regression model for each state individually, and each dot on this particular plot is the state beta coefficient. So it's the beta coefficient for the probability of being voting age and being white. And there's 118 million whites in the data set, and each panel is a different value of epsilon. So for whites, even for small values of epsilon, the coefficients are essentially the same for the original data and for the noise-infused data. As we look at different subpopulation groups, so here's the coefficients for African Americans. Here you start to see more variation. You start to see cases where there are negative coefficients at the state level from the noise-infused data, and we have positive coefficients for the original data. If we look at the American Indian and Alaskan Native counts, you can start to see some real outliers, especially on that second, the 0.50 panel. We've got a number of cases where the coefficients are negative 0.7 from the differentially private data and negative 0.1 to 0.12 from the true data. This is the coefficients for the Hispanic counts. There's 2 million of them. Similar to the whites, not crazy. And if you start to do those interactions, the black and Hispanic, all of a sudden all bets are off looking at these coefficients. The best fit lines are almost horizontal in a few cases, and negative in other cases. So those outliers are really pulling that line down. And so I wanted to get through mine so I can give Quentin enough time to do his thing. So again, the conclusions to take from this, I think, largest impact is going to be on the accuracy of small areas and small subpopulations, and that might be that's what census wants to do.